off. These are our Lyrays, which are some of our standard candles that we use. And if we spread the colors out, and by the way, this is a picture from New England. This is from Lake George about 2 months ago. One of my family members lives up there. We get to see an as-if fifth dimension. I love, just to start, the qualitative beauty of this, ignoring the black spots, just the way the colors transition so gradually. I mean, no artist could paint something that had that smoothness of transition. It's a beautiful, beautiful view. And these spectra and these lines reveal a barcode-like that can tell us something about the star. So I'm going to spend a little bit of time today talking about history and science, and then the remainder of the time showing you examples of things that amateurs like Conrad and Greg, both well accomplished in the field, have been able to do. There's lots of things that these barcodes can tell us. Of course, they can tell us something about the composition of the star. Oops, wrong direction. They can tell us something about if the star is moving towards us, whether it has any radial velocity or away from us. About 80% or so, who knows where that number came from, but certainly more than 50% of the amateur or of the professional publications are done using spectroscopy in the world of astronomy. So even if you're not an imager, even if maybe you're an imager but don't care to get into this, I hope to convince you otherwise. Even if you're just an armchair astronomer, I think what you'll find is that by understanding some of the things I'm going to talk about tonight, your exposure to the stars and to the readings will get that much more rich with the understanding that you bring. I'm going to show you an example tonight of stars spinning and how that changes their spectrum, as well as, of course, their temperature and their information on the HR diagram as to what part of their life cycle they're in. And, of course, how far away stars are is a continuing saga. As is the whole field, things change fairly quickly. But there are some underlying themes in my presentation tonight. I'm going to race through these pretty quickly, but I think you'll see, I was thinking, up until several weeks ago, I was just moving past the slide. I didn't have it. Then I realized I'm trying to communicate certain ideas. You might as well know what they are. One is that you might want to capture star spectra if you remember that thrill of the first image you took of the moon. I don't know about yours, but mine was overexposed, unfocused, tracked poorly, but that was the most beautiful image I had ever seen. And I was showing it to my wife, my friends, colleagues. So you may have had that experience, but after a while, the brain being a novelty engine as it is, it got a little flat. And I found that by jumping into a new field like spectroscopy, I rekindled that thrill for the field. You might want to do some science. Maybe you want to just duplicate some of the science that's been done or contribute new science to the handful of pro-am projects that are going on. And you might want to capture star spectra if you want to try something new, but like me, you're adverse to a big investment. A few weeks ago, an amateur said, well, I'm thinking of buying a new telescope. He had this new expression I hadn't heard before. It was, but I have to talk to my credit card scrutinizer. And I went, what? And it was a spouse that he was referring to. So many of us have those scrutinizers, but this is really inexpensive, as you'll see. I think one of the most significant things that happens when you get into spectroscopy is when you own the data, when it's yours, you're much more interested in understanding it than just understanding a photograph in a magazine. And actually, for me, I've read about things over the years that have gone in one ear and out the other countless, dozens of times, not dozens, half dozen times. My brain isn't quite that sieve yet. You'll remember a lot more if it's your data. And you might want to do spectroscopy if dark skies are hard to get to for you. And because spectroscopy is much more immune to urban light pollution than other imaging. Now, for me, I don't have a PhD in statistics or astrophysics, and I don't have an undergraduate degree in science, but I found that because I wanted to understand more, that spectroscopy was a great direction to have taken. And for me, and probably for some of you, I don't have the patience, the skill, the equipment, the dark sky sight, or the interest in doing some of those long integrations that are such gorgeous images. I'm glad other people do, because they're wonderful to enjoy. But I'm going to show you things tonight that you can do with a video camera that's capturing frames 4 times a second, really short exposures. And I break everything I touch. I am not a do-it-yourselfer when it comes to hardware. And what I'm going to show you is is just the opposite of that. It's just you screw on a lens and you're good to go pretty much. In fact, my favorite menu in Windows programs is Edit Undo, you know, Control Z. Because I can't break things. I can always go back with that command. Sometimes I wish there was an Edit Undo in life. Wouldn't that be wonderful? So you might want to capture star spectra if you want to do some really colorful outreach. I think you'll get a kick out of what I'm going to show you for that purpose. Or if you want to mentor students. And finally, one great reason, somewhat tongue-in-cheek, that you might want to capture star spectra is if you want to hang out with a cool crowd. Now, that's not me, I assure you. I'm a knuckle-dragging programmer. But there are literally between 5,000 and 10,000 amateurs doing spectroscopy with their telescopes now. And so there's a huge community. And, you know, with many of us, we're a little older, and maybe we did our primary learning of astronomy back in the previous century. God, that sounds a long time ago. And back then, it was hard to learn because there wasn't an internet. Now with the web and the forums that are online, things are so much easier to learn. So there's much less of a steep learning curve. So let's do a little history here very quickly. Sir Isaac Newton observed that using a prism, he could split white light into multiple colors. You can also do that by reflecting light off of a finely lined surface or passing it through a piece of glass that is finely lined. Those are all examples of diffraction. Fraunhofer, about a century ago, invented the spectroscope. Here they are looking at the sun. They didn't know what they were looking at, but they knew that it was something that could become important to science. They wanted to understand it. But before we go ahead in time, let's go back in time 500,000 years ago. So this is a fossil laid down by a particular creature that Professor Parker here thought, you know, that looks like the finely lined surface of a diffraction grating, like that DVD we just saw. So he said if an animal had that for its shell, it might look like this. And he said, you know, there was a huge explosion in diversity in life forms back in that era, the Cambrian explosion. And he said that you need to, you know, evolving different appearance doesn't help unless it gives you an evolutionary advantage. And so eyes must have co-evolved during that era. So it's an interesting bit of history. So now we get into the meat of the history, and that is, of course, our buddy Bunsen, who invented the Bunsen burner that most of us are familiar with. He did that to burn samples, put the light through a grating, or in this case, a prism, and look at the result. He was a real pyromaniac. He burnt everything he could find, and he cataloged it, and he found differences when he was burning things. This guy over on the right, Kirchhoff, was a contemporary and fellow researcher. He helped in this process, and he also formulated some rules to explain some of the things we observed. We're not going to get into a lot of depth on this particular part, but I want to point out that there's two different types of spectra we'll see tonight. One has a rainbow with gaps, and the other is completely dark with lines. The interesting thing about these is the lines are in the same position regardless, and which one you get depends on things we won't talk about tonight, like what's the temperature of the gas and any gas clouds that the light's going through, things like that. So, but we'll see examples of both absorption and emission spectrum tonight. So here's some examples of chemical fingerprints. Look how different the hydrogen is there. Hydrogen has a bright line there, helium doesn't. In fact, the hydrogen lines are so important to us that we've given them a name, the hydrogen bomber lines, and we've actually named each line with a Greek letter, like we named the stars in the constellations. You're going to become good buddies with this hydrogen bomber series or lines over the next handful of slides tonight. But they're like a lighthouse or a beacon that help us navigate and find our way around. So here's an example, and this will be the only chemical, well, there's one other chemical slide tonight that we see. I wanted to show you hydrogen. There's our hydrogen alpha, hydrogen beta, hydrogen gamma. But look over here, helium has completely different lines, right? So this is just an example of how lines can differ depending on the element. Here, for example, is your lithium. That would be the batteries in your cell phone if you were to burn them or they burn themselves, and so forth. So today we don't have to be the pyromaniac that Bunsen was. We can actually use a gas tube that we heat with a power supply. And over here on the side, over here, I've got one of those that a little later I'll show you a demonstration of. And we'll also talk a little more about that graph on the right. So In fact, one other thing, if you're an educator, this is a little camera that we developed for educators to look at gas tubes in their classrooms. It uses the same software. Some institutions, like the University of North Texas, that we developed some labs with, they run, this is a mind-blowing number, 2,000 liberal arts students a year through a lab that uses this little spectrometer. It's remarkable. Oh, back to that poster. If I tell stories like this, I'm going to run a little bit over, but I thought I'd tell you that, or brag a little bit, that Neil deGrasse Tyson has one hanging over his desk in his office. He told me this. Now, when I gave him the poster, I'd been standing out in the rain outside the theater here in Seattle for about 3 hours. He came out and I had it unfurled, and he went right to his limo, and there were about 6 of us out there behind a Jersey barrier on the sidewalk, and he was dragging a little bit. And we were saying, oh, Dr. Tyson, come on over. And he came over, and as he's walking over, he looked at it and went, brilliant, that's brilliant. Paused for a beat and then said, can I have one? Well, my wife in her wisdom had sent me with a tube that had one of the posters in it that I gave it to him. Now, I had hoped, and also had my business card taped to it with special tape that wouldn't mar it. I had hoped to at least get an email back from him. Bupkis, nothing. He's a busy man. He's a celebrity, I know. I saw him a few years later in the same context, and that was the first thing he said to me. I've got your poster hanging on the wall. He's got 13 million Twitter followers. That's my not so hidden agenda. 13 million. If he was to shout out our poster, it would no longer be my wife and me, my wife and I rolling up some posters in front of the TV every night for 10 or 15 minutes and stuffing them in a tube. We'd have some high school kid in a garage stuffing posters. Okay, just a little bit of color. In 1835, and pardon the jumping around a little bit, this French philosopher said, we're never going to be able to study the stars. They're too far away. But several decades later, all these guys were doing that, and they were doing it using spectroscopy. And most of them, now I've lost my mouse. Give me a second to find it. There it is. I don't know what happened here. Give me a second. Here we go. So you may recognize some of these names: Italian, UK. The French were really big in spectroscopy and continue to be in the amateur world also. So again, things change over a series of decades, and you have to wonder, what would it be in 10 or 20 or 30 years that scientists might say about things we were ignorant of in this day? I mean, would it be fusion power? Will it be some sort of biological breakthrough? We certainly need as many as we can get. But it's interesting to think about how paradigms shift and things become different. Now, every single individual I've shown you a photo of so far has been a white man and also old. So I'm going to show you some women really briefly here to give you the context of history and to give credit where credit's due. Annie Jump Cannon and her team of women were prohibited from using the telescope, even though they were well qualified, because of their gender. What came out of that was they spent a lot of time studying these plates of spectra. And by their diligence, their attention to detail, ingenuity, and brilliance, they observed and came up with a coding system for star types. So today, our coding system, O be a fine G, kiss me, goes back to the work that they did, which is remarkable. A little bit more current is Nancy Grace Roman, after whom a major telescope was recently named. She was the first scientist involved at NASA, and first astronomer involved at NASA. And her pet project that she drove, her vision, was the Hubble Space Telescope behind her there. She made it happen. And a woman, a contemporary of ours today, Elisa, is an exoplanet researcher. She discovered an exoplanet surrounding a red, or orbiting a red star at just the right distance, the Goldilocks distance, that it could have liquid water on it if it has any water. So there could be life there. So here's some examples of some of the peoples upon whose shoulders we are standing. So how do we get, just to finish up the science piece, how do we get these absorption and emission lines? Again, I apologize for the motor mouth here for moving fast. I want to get us all to the same level and move into the fun stuff. Most of you are familiar with this and probably can explain it in a way that it's better. Niels Bohr's model of the atom has concentric shells with electrons in numbered shells that jump between those shells. And when they jump, they emit energy, and some of that energy is visible. So when an electron jumps from shell 5 to shell 2 in hydrogen, it generates this purple what's called hydrogen gamma. When they jump, for example, between shell 3 and 2, you get this red hydrogen alpha and hydrogen beta. Our friends, the hydrogen bomber series, especially as hydrogen beta at 4861, we'll be seeing a lot of. I love this image of Einstein with Bohr. Look at his posture. I mean, he is kicked back. He is really relaxing there. And I joke with kids when I show this slide in person that, you know, when the next time their parents tell them to sit up straight, and there's scientific evidence that that's good for one's attentiveness as well as thinking, that they can just say, look, Einstein, he was really successful and bright, and look what his posture was. And then I cue the parents that they can tell their kids, after you win your first Nobel Prize, then you can sit any way you want. So here's some examples, some spectrographs. The one on the right is in southern France, and it's a beauty. It discovered the first exoplanet, this one. There's also a star party for spectroscopy people that once were freely circulating again. You can see I stumble across those words because it's such an emotional topic for all of us. That star party is a wonderful one to go with. You can stay in a small French village in Provence and eat fresh French croissants for breakfast and rub elbows with people doing really exciting stuff. It's a great trip. Here's the last of one more spectrograph after this. The reason I wanted to show you this is because it's an enormous instrument, as you can see when you compare the instrument size to the humans there. That's down in Chile. So this is the space shuttle servicing the Hubble Spectrograph. And my son looked at this, and when I told him what it was, he said, no. He said, that's a refrigerator, it's filled with beer. And every night on the space shuttle, you know, when the video's off, and of course there's a lot of nights on the space shuttle in 24 hours, they're party animals. They're you know, having fun. I can't prove him wrong, but I think he might be. So this is a friend, Dale Mace's amateur, his setup. It is complicated and expensive, and we need not go to that degree of complication and expense. One thing I love about this is this gas tube. It looks like he just jammed it in here. Now he uses that for some calibration steps. What I really like about it is you know, you see that those two pins there at the end of the tube. Now, you know, these things require high voltage. So I picture Dale at night. He's got two alligator clips with high voltage. I suppose he's got gloves on. And, you know, as he pins those on, if he accidentally draws a spark, he's going to ruin his night vision, right? So, but fortunately, there are things that are a lot less complicated than this. And what I wanted to show you examples of tonight is this grating here, the Star Analyzer 100. It's an 1.25" grating, screws onto most cameras, and we'll talk a little bit about that in a moment. And while we're talking about that, let me see if I can get the camera over to that gas tube, turn it on, and hold the grating up here. See that spectrum going in over my head? It's actually multiple spectrums all in series with one another, but the green and the red and maybe a little yellow at the top. So that's all this is. This is just like a prism. It just splits the light into its component colors. So here's an example of how you could use a star analyzer. Again, we've got the grating screwed onto the lens cap threads of the camera, and notice there's no tracking. Now, even without tracking with a small aperture, there's hydrogen alpha, hydrogen beta, hydrogen gamma. This is not all that easy to do. It's not expensive to do, but without tracking with the small aperture, it can be a challenge. It's a drift spectrum, and so we don't recommend people get started this way unless a telescope is out of the question. Just wanted to make sure that light was off. Here's some more common ways of mounting a grating. You saw this in the previous slide. One of the things that we do is we sell this little adapter that threads onto the lens cap threads of the camera. This is called an objective grating because the starlight goes through the grating before it goes through the camera lens. You can put a grating on almost any camera, a fixed camera, mono, color, cooled, not cooled. You can do it on a ZWO. In fact, Greg's got one of these cameras, a ZWO camera. And down in the lower left-hand corner, you can see a grating or a filter wheel onto which we could put a grating if we had one. So there are more expensive devices. You can see the price point there. And the difference is these have a little slit. We're not going to talk much about these tonight. I'll give you an example or two and show you how they work. But you know, the challenge is, first of all, the money. Talk about your credit card, what was that? A scrutineer. I love that word. So let's sort of like mutineer. You don't hear a double E-R on the end of that many words like that. So it's got a narrow slit that's like 20 microns wide, and you have to guide on that and find stars on that. They're a lot harder to use. I think maybe 1 in several hundred amateurs go right to these. Almost everybody starts out with a grating. So some do both. Here we've got the camera on top of, piggybacked with a grating on the nose piece, as well as one of those expensive devices here. So this guy, and this was Robin Leadbeater, is doing both at the same time. Okay, we raced through all that theory. Now let's talk about what we can actually do. So we have the starlight coming down, it goes through the grating, and it creates a rainbow that falls on our sensor. Here's our first really fun example. Now this was done by Torsten Hansen with an 8-inch Newtonian and an imaging source video camera. And each of these is a different spectrum captured at a different time. They're in temperature order. So the hot stars are up here and the cool stars are down at the bottom. So in Obeah G kiss me order, we can see the B and the A and then F stars and then K and M. So look at those spectra for a second. They're remarkably different from one another. So now we can tell star type approximately by looking at the presence and absence of gaps in these spectrum or absorption features. Specifically, look how this gap, which is the hydrogen bomber beta line, is wider and darker than the gaps above and below. In fact, there aren't any of those down here on these really cool stars. That's because these type A stars are the ideal temperature to pump those electrons between those two levels. These stars at the top are too hot. A lot of those electrons in the hydrogen just get blown all the way out of the atom completely. They're gone. And these stars are too cool. Some of the atoms don't get pumped up to that level. And these stars down here are so cool, we don't see any transitions between those two lines and those orbits in the atom. So the other feature I want to point out here are these really wide bands. Now, I'm broad but not deep. I'm going to tell you everything I know about those bands. And Conrad, please don't leak this onto our forum. I wouldn't want to lose whatever shred of authority I've got. I've boxed in here one of those bands. These are molecules in the gas shell of the star on the outer layer. The star is cool enough that they're not broken apart by the intense heat of the hotter stars. Those are molecular bands or titanium oxide. You want to know more about it, the web's your friend, as of course is Wikipedia. So if we have a star and we've got a grating and a spectrum, see that crosshair I put right there? So can you see that right in the middle of that crosshair up there, there's a little bit of dimming? It's a little, the color's a little different. You may not be able to see it on your monitors, but I'll tell you, that's not the way to do science. For me to write a paper and say, oh, we observed Vega at such and such a time with this telescope, and we saw a little bit of dimming sort of in the robin egg blue area, that's qualitative. If we want to do science, we need to have numbers and measures, and so we graph it. The graphs are pretty straightforward. This is an intensity graph. The star is narrow, so this peak is narrow. The star is very bright, so this peak is very high. Same thing over here. This thing is wide, so this thing is wide. And the great thing here, oops, I fell out of the show again, one extra escape key. Let's get back to that slide. And that is there, is we can now see in that intensity graph down here, that barely discernible dip. Now we can measure its width, full width half maximum, its location, what color is it, how does it compare to others on other stars, on other dips on this star, and so forth. And that's how we do spectroscopy. The graph is pretty easy to use. I'm going to show you examples of that going forward. So, I was going to tell you a little bit about my history. So I went out about 10, 12 years ago with a grating, and I was all excited to do spectroscopy. I had my C8 in my backyard here in Seattle, 3 miles from Pike Place Market. I captured some spectra of Vega at midnight. I came in. Of course, my blue jeans had grass stains on the knees because it was Vega and it was overhead, right? So I did not have a particularly sophisticated mount on my C8, just the stock factory mount, the Celestron mount back then. And this was in the early 1990s. So the next day I tried to do some spectroscopy with software. I tried to take the images I captured and view them on the freeware that was out there. And after about 2 hours, I'm not exaggerating here, I gave up. I just shut it down. I was so frustrated. The software was crashing, it was buggy, half of it was in French, there was no user manual, and it just didn't have the polish that a modern application should have. So I put the grading in the drawer and I gave up. I told my wife, this is a hobby, I'm supposed to be having fun. I don't want to fight software. But I really wanted to do this. So about 2 weeks later, I thought, it was like a Saturday, I thought, you know, I can write a program that does that. That won't take so long to make that graph. And so I'll do it tomorrow. And I did it tomorrow on Sunday. And then I got this graph, of which this is the example. This is my first spectrum, first time out. And now, say 5,000 or 10,000 hours later, the software is almost done, just a little bit more. That's the way it is with software. So this is my software. I want to spend 2 minutes max, maybe 3, showing you the software because I think it's helpful to see how easy it is to use. So over here, we have the star and the spectrum. This one is in color. It could be mono, which would be a little brighter on dim stars. And we simply just bracket in the area that we want to study with these orange lines. And over here, we have that graph. So this here is that broad or sharp peak for the intensity of the star. And this data is over there. And if we look closely, we can see a little gap there. That's that dip, which is water in the atmosphere, as well as a lot of other dips. And now, you know, the devil's in the details. I got to this point and I went, oh, now what? How am I going to know what those dips are? So the great thing is not only are there communities that help, but Bunsen created a catalog, right? He burned hydrogen, he burned helium, he burned all these things and created a catalog of lines. Now those catalogs have been refined and expanded over the years, but here's that catalog. Here's some of the elements in that catalog. You can see some are listed here, and I can say to the software, show me where those hydrogen lines that Balmer found and that Bunsen found, Balmer explained, I suppose. I don't know why it's called Balmer. I imagine there's a scientist involved. There's the wavelengths, which you don't have to know. And when I click this, it overlays this blue template, and now we can see the software. There's hydrogen alpha. Look, oh wow, there's a dip there. Hydrogen beta, hydrogen gamma with a dip there, hydrogen delta, and that's all the Greek I know. So now we've more or less conclusively proved that we're finding hydrogen on the star. That's how we know not only what it's made of, but something about its temperature, because it can't be one of those cool stars if we're seeing all that hydrogen, because the hydrogen lines don't appear on cool stars. This is very cool. And in fact, just to show you something interesting, this is actually a video. If I turn stacking off, you can see this is changing. It's a video recording I made under the stars, playing at 2 frames per second. Look at it jump around as our scene changes, right? And some of these features are clear and others aren't. Let's zoom in on this hydrogen alpha. You can see that dip come and go, right? I'm going to turn on stacking in the software. Watch how that dip sort of magically appears after only 5, 10, 20 frames. Here it comes. It's getting stronger, clearer, then it's stabilizing. So at 2 frames a second, it took, what, 5 seconds? So 10 frames worth of stacking, and now very clearly we can see that feature. So that's all I want to show you in the software. I'd like you just in your mind's eye to just remember what this looks like, this view. Not that I'm going to quiz you, but just that there's some lines are getting closer together. There's some up in the red, because we're going to look at that one more time as we continue. So let me minimize this, jump into the show, the PowerPoint show again, and give me a second to get back into that. Okay. So here's an example of a DSLR image. You can see this star here has some very bright emission lines, as does this one. But this one has a broad absorption line. So you can get either on stars, as I mentioned earlier. So in 2011, Janet Simpson sent me this DSLR image taken with a 30-second exposure and mechanical tracking, like those Skywatcher, you know, just the mechanical tracking. And I have a confession to make the group. I couldn't remember what a Wolf-Rayet star was. And I mean, I'd read about it, you know, a half dozen times, but you know, things go in one ear and out the other. When you have data that you care about, like it's your data or data somebody sent you, that changes everything. Wikipedia is your friend. It turns out these are late stage stars where the outer shell is no longer there. The hydrogen and the other simple elements that we'd be looking at, but what we can see is carbon, carbon, carbon. It's like soot. We're looking down towards the core. We're seeing the byproducts of the stars burning with a backyard telescope. Now, some other interesting things that we can tell from this data, and that is that these are very wide peaks. That's why we can see them with such simple gear. And they're wide because Wikipedia tells us these stars have intense stellar winds, and those winds broaden the features. Okay, let's look at another example here, our beloved Ring Nebula. That's not nearly as interesting, is it? That's because this grating doesn't have a slit. And without a slit, most extended objects are pretty boring. This is one of the only interesting ones. It's got two elements only, right? It doesn't have a continuum of lots of different colors, hydrogen and ionized oxygen. But for the most part, to look at extended objects, we need to spend that $2,000, $3,000, $4,000 or 3D print one for $600 or $700 to look at an interesting spectrum. And I want to show you one of those of a second beloved object of ours, M42. You can see the same features. There's our hydrogen, there's our ionized oxygen, but those are really narrow features. And the reason they can be so narrow is because we're using a slit spectrometer. So I'm going to turn off screen sharing just for a second, because I'd like to ask the group here, and it's a good group. It's a good number of people. And just out of curiosity, I'd love to hear one or two of you. You can just hover over your image or your name and click unmute if you want to. Just tell us as a group, the first time you saw M42, the Orion Nebula, where were you? What was your experience? Anybody want to tell us? I'm sure somebody. Bueller, anyone? Anyone?
Hello?
There you go. Hi, Steve.
Hi. I don't remember the first time, but I remember after I completed work on a 16-inch mirror, the first time I saw the Orion Nebula with that, and I'd never seen the intensity of the colors and the amount of detail and so forth. That's always kind of stuck with me, and the green, the strong green component to it visually.
Sure. That's a great story. 16-inch, you're teasing us here, Steve. Not all of us have that kind of aperture. Anybody else, first time they saw M42?
Yeah, I was in high school. We had a very, very small high school astronomy club.
Right.
And only one of our members had a telescope. And it was an RV6, and we used to go out into a farm's field, not too far from Seagrave Observatory, about 5 miles away.
It was our first date.
Now we're getting into the interesting part.
I didn't know where we were going.
Yeah, you want to come home and see my telescope? That's what he was saying.
And so that RV6 was the first instrument that Kathy and I saw M42 through.
What did it look like?
At this point, I really can't tell you.
I hear you. On a 6-inch, you get an idea what it's going to look like, and that's what I was fishing for. Yeah. But
my first experience was through an RV6, and much diminished conditions. It was from the roof of the science building at Wagner College on Staten Island, and you could see trapezium, no problem. We're using like a 12.7 millimeter kilometer, I guess. You could see trapezium, but you could just barely make out what looked like a jellyfish-like pale shroud around it. And with much averted imagination, you could build up a little bit. So much to my surprise, with the same scope, a month later, I was in Batstow State Park in South Jersey. And to look at that again and see its wings extend across the whole field of view.
Yeah.
And the trapezium was lost in it. It was just amazing.
That's a great contrast. That's a really interesting story. By the way, Scott, you may be using a different mic than you think. That was a little bit, we could certainly understand it, but it was a little overmodulated. Maybe you're using a webcam mic instead of your mic on a stand or something. No big deal. Okay, I'm going to go back to sharing my screen.
Turn it down?
Yeah, maybe turn the audio down a little bit, the audio levels. Okay, let's pop up that show again. The reason I asked that, and Steve sort of came through for me, or Scott, excuse me, Scott came through for me. My experience was really a disappointing experience. First time out, early 1990s, getting ready. I mean, I was excited about Shoemaker-Levy 9, queued up in a observing football field in Denver. who, by the way, also have an Alvin Clark refractor in their observatory. And my eyes were so unaccustomed to what I was seeing that all I saw in that observing field, you know those cannons that in the circus they used to shoot people out of? That's what I saw. To me, what are they doing here? Those were Dobbs, of course. I queued up. Somebody like you all or me was, managing the telescope, talking about what we were seeing. I was so excited. I got up there. It was a smudge. It was nothing like I was expecting. I was really let down. I was disappointed. But I'll tell you, like many of you who may have had that experience, I came back to it and still do repeatedly. What's changed? It's still a smudge in my telescope, especially here in Seattle. I think what's changed, and I think you'd agree, is that now I understand. And when we bring that understanding of what we're seeing to the telescope, it becomes a much richer experience. It's an experience that, we bring more to it than the photons that hit our eyes. Now, of course, the other thing is we're much better at averted vision. And here, this is my latest invention for averted vision. You may think, that's sort of just silly, but look, I'm now looking off to the side, and I've got vision over on you all too. So it's a nice observing aid. But kidding aside, the depth of understanding that comes with learning a little spectroscopy helps us in our other activities too. So this is Uranus and Neptune, also done by Torsten Hansen. Look at these spectra. You can see visually very easily some very broad gaps. There they are graphed in the software. And we're looking at the methane lines of these planets. Now, 20, 30 years ago, if you told a professional astronomer that with an 8-inch telescope and a video camera, you could capture the atmosphere of these planets, they would have given their left leg, right, to be able to do this kind of thing. It's pretty remarkable what's possible. So again, I keep saying beloved when I refer to these things because these are all our beloved showpieces, right? So Alberio A and B, there's not a lot to this slide, but I want to point out that Alberio B, the blue one, has much more energy over here in the hot blue end of the spectrum. And this gold one has a lot more energy over here in the right. I sort of had hoped that this spectrum would have had much higher peak here. And this I can't remember. Ken White, I think, is the one who created this. I was just getting worried because I was afraid that it might be Conrad's and I wasn't giving him credit. I need to figure out who it is who gave me this spectrum. So in 1881, Henry Draper captured the spectrum of a comet. Hey, listen, if Hank can do it, so can we. Here's an 80-millimeter refractor with a Canon DSLR. There's this like little string of jewels, and there's the spectrum there of the swan bands. And at this point, some of you may be saying, wait a second, Tom, a few minutes ago you said you can't image extended objects here like M57 without a slit. Well, this is an extended object, but fortunately it's fairly compact in the core, and he was able to tease out a spectrum from it. So now anybody who uses a C-clamp as part of their equipment, that's my kind of do-it-yourselfer. Robin Leadbeater set this up. He's the designer of the Star Analyzer, by the way. And he put a grating on the nose piece of a video camera, and he captured, this is a single frame. So during that frame, the meteor moved that much distance. That's it right there. And at this particular moment, it brightened. There was a bolide, and he captured the spectrum and tentatively identified these minerals. Now, this is sort of an esoteric sub-branch because it's a nuisance. You've got to capture a meteor, first of all. You spend a lot of time waiting. But it's something that some people love, and if it floats their boat, I'm delighted for them. So I'm not going to spend much time on the flash spectrum, except to point out that yellow was how we discovered helium. And also, as many of you know, the reason we can use a slitless grating on the sun is because just before totality, the sun, if you look in the lower left-hand corner, is a very narrow object, as if viewed through a slit. There's the helium that we discovered. It's a great story. Most of you probably know it now. So you can capture the spectra of novae. Here's a nova that has iron, captured on a Canon DSLR, but here's one that doesn't have iron. So you can discern, I don't know if the word's morphology, but you can discern the differences between different novae. Really quick review of Doppler shift. You're probably all familiar with it, but just to make sure we're on the same boat, sinking as it may be, the Doppler shift is a change in pitch, for example, that sounds makes as they're coming towards and moving away from you. Like a train whistle going through a station, it goes, right? Coming towards you, coming towards you, coming towards you, going away, going away, going away. High, low. Light does the same thing. Suppose we were expecting to see some spectral lines on a particular object, and instead of them being there, they were all shifted to the right. Well, that would reveal to us if there's some Doppler shift going on. Well, what about if they were shifted to the left? Same thing, that would be blue shift because it was coming towards you. So let's look at a supernova here. Again, really briefly, this is one particular type of supernova called a 1A. All of you, or many of you, are familiar with it. Two stars circling one another more or less. One of them is a red giant. And now I need to go back to this show. It says it spills gas onto the white dwarf. I hate that word spilling. That sort of gives the predominance to the red giant. It's sort of like what? It's like spilling water out of a pitcher. In both cases, whether it's water or the gas in this example, I think it's more accurate to say the white dwarf's gravity drags that gas in. And what happens when you throw gas on something hot? It explodes. We get a type 1A supernova. There's a supernova in M101. There's an image of a similar supernova, but not this one. Look at that gas cloud as it expands. I love that image because even though it's 2D, you can see that, well, you can even see through it in some places, but certainly not along the edges. You can see, you can sort of guess, oh, that is a sphere. It's not just a circle. So David Strange used a C8 to capture this spectrum. He did that with just a C9, excuse me, just 15 minutes or less of integration time and stacked. And this is the spectrum he got. And the cool thing is that he expected and found a deep dip around 6,000 on the x-axis. Because the shoulders upon which we are standing, some of the heads on those shoulders have told us that a type 1A supernova is going to have a really deep dip there that should be somewhere around 6,000. So David dutifully figured out, hovered his mouse and figured out, oh, okay, that dip is right at 6150. Cool. Now stick with me on this next 4 lines. So we wanted to know how fast that supernova was expanding. Well, that's the number that David Strange measured, right? That's 6150 down here. Now, if Bunsen had burnt beach sand at a stationary location, he would have found the line there. It would have been like over here. So again, I don't know what the Doppler shift formula is off the top of my mind, but Wikipedia is my friend when he sent me this. You plug the numbers in, and you now can see the blue shift of that shell coming towards us with 15 minutes or less of integration time on a 9-inch telescope. Wow. And that's a big number, by the way, 22 million miles per hour. Pretty amazing. Now, some of you may recognize this guy who got the Nobel Prize in 2011. He and his team, right before the turn of the century, boy, doesn't that sound like ancient news? It's just 20 years, right? So they used type 1A supernovae like these, like this one, to measure cosmological expansion accelerating, and he won the Nobel Prize for that. He also answered an email about an article I wrote a year later, and I'll show you that, actually a year before, if we've got time. We're going to keep moving pretty quick here, maybe not now. Here's another example of day by day, the change in a supernova. Again, you can see the deep dip here. It should be over here. And as time goes by, it broadens, gets more diffuse, and seems to migrate over towards the line there as the shell gets more and more diffuse. Okay, what about a black hole? You know, the core of a galaxy. I've never seen 3C273, our brightest quasar, but David Hayworth from Portland, Oregon had, and he captured the spectrum there. You can see 2 little dots of light, which we blew up to here. There they are. You'd almost miss them if you weren't looking for them. And there's the graph. Now, in the mid-1960s, Martin Schmidt was in his mid-20s, and he stared and stared at this and could not figure out what was going on. He was very frustrated, and the reason I know is there's a wonderful transcript, a link to which I can send you if you ask for it, of an interview with him where he describes the discovery I'm about to describe very briefly. He was very frustrated. He'd spent days looking at this, trying to figure out, is this the opposite of that silicon absorption line we saw? What is it? He decided, okay, let me get the easy stuff out of the way. I might as well just spend some time, eliminating some things. So he figured, let's get rid of the fact that these can't be hydrogen. So he brought up the hydrogen bomber series. This is the screen capture from my software I asked you to remember. Those are the bomber lines, the hydrogen lines. And he went, nah, they don't match. But then he dug a little deeper, and they did match. They matched, but they were redshifted an enormous amount. The fact that they were redshifted that far meant that this object, using the Hubble constant, was about 2 billion light years away. And the discovery was that something could be that far away and still so bright to our eyes and our telescopes, which means it's intrinsically really bright. And now amateurs can do those same measurements. Now, the amazing thing to me is that this is 2 billion-year-old light, and yet it still has enough information for us to tease out some facts about where it came from, how long it took to get here, and what produced it. That's really amazing. Now, there's other things in the universe that don't age that well. Here's Martin Schmidt a few years ago. Now, I know I'm living in a glass house throwing stones. I don't mean to dump on him, especially as I look at the video of, of all the attendees here. You're all feeling the pain, I know. So, but it is amazing the light that this old can contain that kind of information. So a couple more examples here, literally. So far, we've been looking at features like these bomber lines, these hydrogen bomber lines. I warned you in the beginning you were going to hear a lot about them. Sorry for that. So and how wide are those lines? Let's just take a quick look. Well, this feature is what? It's about 50 angstroms on this scale here. It's about 50 angstroms wide. So that's our resolution. We couldn't see something much narrower than that. If we want to drill down and look at this hydrogen alpha line, we need to spend the money and gain the knowledge to use a slit spectrometer. Now, the moon's in blue and Vega's in fuchsia, and you can see that hydrogen alpha feature, they're not the same. Why would that be? Because Vega is moving towards us, and we can actually measure, just like we did with the Doppler shift, we can measure the radial velocity. And we got fairly close, 20 kilometers per second versus 14. This is my last example that I want to give you. I've got a prop here. Here it is. This is a star that's rotating. My hands are light. It's rotating like that. So what's happening to the light coming off here? It's coming towards you. It's blue shifted. And what about the light here that's coming towards you? Well, the star is moving away from us there, so that light is a little red shifted. So the light coming from here isn't being accelerated one direction or the other. So its speed is normal. And so this is what we'd expect, but we have a little bit of red shift and blue shift. When you do that and compare a star that's rotating fast and a star that's not rotating, you see this. So the fuchsia is Vega and the blue is Altair. And you can conclude that Altair is spinning really fast compared to Vega, and that would be an accurate conclusion. This also requires a slit spectrometer. So this is the kind of thing that people typically step up to after a few years with the grading. Some never do. They say, I don't want the hassle and the expense, and I like looking at the broad field of the whole star. I think Conrad's one of those still. So how do you get started? Very simply, I've mentioned the Star Analyzer a handful of times or more. So any sort of camera that you've got will work fine. Mono, color. Now, sometimes it turns out that it's not like focusing, but this distance between the grating and the sensor and the camera needs to be sort of in a given range. Oftentimes, you can just screw it right onto the camera nose piece and you're good to go. Sometimes you need it a little further away, and so you may need an adapter. But we've got a little calculator on the site, and I'm happy to help people figure out what they need to get started. If I was a good salesman and marketer, I would have mentioned my software's name countless times. Of course, it was down here in the URL. RSpec stands for real-time spectroscopy, because you can do real-time imaging under your telescope, either with video or also with FITS files can be loaded automatically into the software. There's other shareware out there that I mentioned earlier. A lot of people use it and get good results with it. It just wasn't my cup of tea. It's more advanced than mine, so it's really for the longitudinal hair splitting that people who are doing more and more science use. But the learning curve is also quite steep. A couple books I wanted to show you, and then we'll finish up. I'm sorry I've gone a little longer than I promised. My fear always was when I was starting is, okay, so I found some dips. Now, how am I going to know what they are? Yeah, I found some hydrogen dips with that little blue template overlay, but how am I going to identify all these features? Well, first of all, that cool crowd I mentioned earlier in my top 11 list, people love to help others figure out what spectra they've captured. And this book, it's the one rightmost on your screen there, has all these really cool annotated spectra, which in themselves would be pretty worthless for me because, as I said, I'm a knuckle-dragging programmer. I'm not a PhD or an astrophysicist or a science guy. But this book also has a lot of prose aimed at us. It's aimed at amateur astronomers, written by an amateur astronomer, by two amateur astronomers. And the books aren't all that cheap, but they're gorgeous books, and I probably learned more from them than any. There's a books links page on my site that shows those kinds of links to how to buy those. Not that I need to say this here, but I get like 20 cents when somebody buys something having come to Amazon through that link. I think I've made like $34 in 10 years. And I get money. I don't know if you know this about these referral plans that these sites have. If somebody buys anything in that session, I think that's the way it works, I get, a few tens of cents, depending on how much it's worth. So I've made like 30 cents on somebody buying a My Little Pony video about 6 years ago. Hey, works for me. So the cool thing about what I've been trying to do in popularizing spectroscopy is you can download the software for free for 30 days, a fully enabled version from this download link. That page also has a link to a YouTube video of me giving a webinar. No, it wasn't a webinar, live presentation to the AVSO 3 years ago or 4 years ago, walking through how to get started with the software. But not only is a video on that page, but there's also the sample data that we all worked with. And you could do that tomorrow, and you could be processing, our spectra and decide whether that was something you wanted to do. AVSO, whether it's Arnie in the past or Stella Kafka, both professional astronomers, are all over. Meaning that they love spectroscopy. AVSO recently started a spectroscopy observing session. I'm going to be speaking to them as a group later this summer. And they're going gangbusters. They've got a spectroscopy database they've just brought online. There's opportunities, although not that many yet, for amateurs to do a pro-am collaboration. These are all amateurs, except for these two. Bob Stencil is at the University of Colorado. I think that's where he is. He's in Denver. And some others here. We won't get into those details. So in the last 200 or 300 years, on the last 45 to 55 minutes, we've come a long way, right? Fraunhofer invented the spectrometer and first observed these curious colored lines. And then 50 or 60 years later, Bunsen and Kirchhoff studied them more systematically and classified different elements with their unique fingerprints. We all do stand on the shoulders of giants, and it's a wonderful activity. I get enormous pleasure out of helping people get started. I know that some of you in the club in the past, when things have been more open, have been doing outreach, and I want to thank you for doing that. You know how much fun it is and how rewarding it is. All of us here in this meeting, by virtue of the fact that we're here, have had enormous opportunities in our lives and have had the privilege of learning these things. And we can give back by doing outreach. I had a poignant moment, just to chew up another 30 seconds of time. I had my Lunt solar telescope down at the Pike Place Market. Now, they chased me off the market grounds because you need a license, because otherwise there'd be 100 buskers playing music if you didn't have to get licensed and scheduled. So I went across the street to a lookout over Puget Sound. And over there's some street people hanging out. It's sort of noisy. I wasn't all that comfortable with them. I was worried they were going to be scaring away the people I was trying to show the stars to. And one guy was sort of watching me for a while. And a young guy, maybe not homeless, but, sort of hanging with his buds. And he came over and he said, "Can I look?" And, my first thought was, I'm embarrassed what my first thought was. So my first thought was he's going to get in the way of other people who will enjoy and learn more. Fortunately, my second thought was, yeah. So he sat down, and you know how sometimes people look for a long time. It either means they're not seeing anything and they're faking it or trying to see it, or it means they're captivated. Well, he was one of those. I was standing next to him describing what he was seeing, those little arches like McDonald's arches on the perimeter, or, you could drive the Earth through those, all the standard stuff we do when we're doing solar outreach. And he looked up, he sat up from the eyepiece and he turned up and he looked at me and he said, "How did you learn this?" It's an amazing question. I was really thrown off balance and reminded of the privilege and opportunities we've had. So I'd encourage everybody, as many of you do already, to see what we can do to do some giving back. I'd like to thank you all for your attention tonight. There's my contact information on the lower side. I'll be here, as I said, until you drag me off the stage or it gets just too quiet and we start all nodding off. Thanks again, everybody, for listening and for smiling at my jokes.
Thank you very much, Tom.
Sure.
Just to let everybody know, we have been recording this. Jan will be able to put it up somewhere, I think, on YouTube for use of skyscrapers.
Yeah, I'll give it to Jim to put on YouTube.
Yeah,
Great.
Tom graciously gave us permission to do that. Just before we open it up for questions, we do have another online presentation on August 1st. The information is in the skyscraper. That looks to be an interesting talk also about potential interaction of dark matter in the Milky Way, thanks to a Harvard astronomer, Anna Banaka, that's going to talk to us. So if people have questions, unmute yourself, and I guess probably, Tom, you don't mind if we shout them out? We'll try that maybe.
Yeah, let's do it.
That. Yeah. Any questions? Unmute and shout them out.
Well, while you're thinking about your questions, I have another prop which I'm supposed to use in the middle, again, to get a little laughter. This is, this is the bomber series right there. That red there is a hydrogen alpha. It's very hot, so I'm sort of glad I forgot it. But this will give me some authority to answer any questions you may have. So go ahead.
Any questions?
So this is Mercedes. Thank you for your presentation.
You're welcome.
So I'm curious about your last comment. What was your answer to the young man about how you learned all that?
That is the right question. I don't remember. I was embarrassed for the disparity between his and my life experience. And I think I said, I just read books. I found somebody to teach me. I didn't invite him to study with me, and I should have. But I really appreciate your asking that question because that gets to the heart of the story I was telling. Thanks.
Thank you.
And Tom, all of the videos and other materials are on your website for people to investigate this more?
Yes, absolutely. And you can see it down there.
Tom, this is Arthur. I'm curious if there's any changes in the spectroscopy with Betelgeuse, lately because of the dimming.
That's a good question. Hey, Conrad, do you know? Where is he? There he is. You need to unmute yourself. Hover over your face and you can, there you go.
Okay.
Has Betelgeuse changed in the spectrum?
Can everybody hear me?
Yes.
Yes.
Yeah.
Okay. I've taken some spectra of Betelgeuse. I only noticed some small changes when it started to brighten up a little bit. But I'm kind of limited, after a while, it goes on the other side of my observatory and I haven't noticed any, so I couldn't take any more spectra with it. I am able to take some reasonably detailed spectra, and but I haven't seen any huge changes.
Yeah, just to show you the kinds of, I think that's why Shoemaker-Levy was so exciting. SL9 was so exciting to us, as well as other things we see like comets, is because they change so quickly in the scale that we're looking at. And on the site, there is, just to show you the kinds of changes you might have been asking about and may occur for all we know. These are some of the examples on the site that I discussed in my presentation. But what I wanted to show you was, give me a second here. I'm going to go to the top and search for LYRE. LYRE. I know. Oh, there it is. I'm right on it. So this is a spectrum that, this is a frame from a video that a gentleman, Soloccia, in Italy captured in just 2 hours with a 4-inch refractor. Just to give you a sense, and it says click on the image. So this is going to be a little video, but watch the changes that occurred over 2 hours. We'll let it play a couple times. It's just 5 or 10 seconds long. Notice there's no beta hydrogen lines here, and then as things get hotter, more blue at this end, the hydrogen lines become more visible. This is really just stunning. that you can see this kind of change spectroscopically. I don't know with Betelgeuse what we saw. I think they said that they believe that the Betelgeuse changes were brought about by some sunspots, very large sunspots. And I don't know whether we'd be able to see spectroscopically the changes that those would bring about. But again, that's because I'm a knuckle-dragging programmer and not an astrophysicist. Any other questions? Ian.
I'm curious. One of the things I've noticed over the years is that the gap between the spectrum analyzer and the more expensive systems has not gotten smaller. It's gotten bigger, in the sense that fewer and fewer people, companies are offering spectrographs at the next level. And yet, as you pointed out, it's not like one could, in principle, make these things in the intermediate level. Do you know why that is? It would be an easier stepping stone.
That's a good question.
For amateurs, rather than going to the to the HLR.
I think some of it is just the economics of it. There aren't that many of us, and I'm thinking, and I don't think this should be a disincentive for you getting started, because the amount of fun you can have with this grading is amazing. But my sense is that less than 1 in 10 people end up buying a big spectrometer, the expensive ones. I think a lot of people do this for a year or 2 or 3 years, and they go, I've learned what I wanted to learn. It was fun, and they move on. The other thing I'd say is they're now with 3D printing. There's a spectrometer I should have in the show called low spec. Conrad, do you have a low spec yourself?
No, I thought about it, but I didn't want to do it. I'm still been doing a lot of work with putting a grating in front of my refractor.
Oh, that's right. Yeah.
We've had some awful weather, so I haven't been able to do much with it. Yeah. But, going to these nice spectrometers, it is a lot more complicated. And I just did not want to get into that. I'm looking for a way of, getting good spectra without a lot of work and a lot of complexity to it. But no matter how you look at it, even with low spec being created on a 3D printer, it's still complex. Getting it to, and you still need, what people don't talk about is you need a really good mount, okay, for tracking. And that's almost as important as the spectroscope itself. So it just gets expensive. When you see a lot of the photos of the European astronomers, they're not using, Edmund Scientific mounts. They've got some very expensive mounts with a lot of really nice equipment on it. And it just, it's just a whole different dimension.
Yeah.
And I'm looking for a simple but effective way to do it. Putting the grating in front of the scope has been pretty effective.
And Conrad, to blow his horn deservedly for a moment, he's done some really remarkable path breaking and exploration on how to take a grating like this and add a prism to it. And he's actually studied it on a lab bench that he's got there and published to our group some wonderful write-ups and has gotten a lot of respect from the people who know the field far better than I do. It's always exciting to see Conrad's posts because they have so much interesting information in them. The other thing I'd mention, again, we're short on time, so I won't ask one of you to grab one of these off the shelf, but I could. And then you'd believe that it wasn't a setup. But, sort of like a magician who asks for a volunteer from the audience that's their confederate. But, in the backs of these magazines, they have these gorgeous images, like this one that looks like a rectangle. In fact, they call it the box. And this was taken by Bruce Waddington. I love these beautiful images. But then you look at it, it's 10 hours of integration time. I don't have the equipment, the skill, the time, the interest, the dark skies to do that kind of thing. So I think that it gets more and more rarefied as you go up into those. It's a really good question, Ian, and I've thought about it. I sort of provide this entry pathway to people. And I think that as the years go by, especially if the AVSO can generate the kind of interest that, frankly, they haven't been able to do over the last 4 or 5 years. which is an interesting point in itself. And I don't know why that is. You know, Arnie and I did a sale of our products with some discount a few years ago, and you know, we had 20 people buy them. For some reason, it hasn't gotten traction with that community. And I think it may be, well, I don't know. But one thing I'd observe is, and this is what I was going to say, is that it's so different. It's just a different way of thinking. Photometry are just single points over time. This is a lot of points at one moment. And also the photometry people, they're committed, they have a track record, and their equipment's set up to do photometry. And so they don't want to be messing, taking things apart, putting gratings in. But it's a good question, Ian. I don't know the answer to it other than what Conrad and I just said. Any other questions? Now, I have a question. Is that really Robert Horton's photograph there? It's a gorgeous photo.
It is. That's really what Tom looks like. What Bob looks like, I should say.
That's really great. Now that I've lost it,
He doesn't really.
I don't know where it went. I'm going to
He's
stop.
got that kind
sharing it so I
of
can
he's got
see
that
it.
kind of waxy complexion, I guess.
Yeah.
Yeah.
That I won't go there. I don't know him well enough to pull his leg quite that hard.
No, that's good. You can do that. It's fine.
If anybody ever has a question about RSpec or this type of spectroscopy, because I'm a lot easier to get a hold of than Tom, please shoot me an email. I'd be happy to work with you on this. You know, I've been doing this for over 8 years, and I've enjoyed it a lot, without a doubt.
Tom,
And, yes.
one of the things I think I remember hearing is that it's one of the best stars to get started with is Vega, because that's the good. It's probably one of the
It's
better.
an A-class star with
Right.
very bold hydrogen bomber lines. So
Okay.
you can't miss it. You can't miss it. It's easy to focus with, and
It's a good standardization.
yeah, it's a standard A-class star, and the lines are bold. You can't go wrong with it.
Okay.
Yeah. It's interesting because you have the advantage of Conrad, and you know him, and he's local, and that's a fantastic offer he's made to you to help. I spend a lot of time helping people. I thought I'd show you this. So this email just came in, just to give you an idea what my life is like, and it's a good life. I enjoy the heck out of doing this kind of thing. I'm just going to share the screen briefly. I know you've got other meeting business to do, and that is, can you see that email there?
Yeah.
Yep.
Okay, great. I'm sorry, I can't see any of you nodding your heads. So again, this guy's saying he's learning spectroscopy because he wants to teach his grandkids and nephews. But what I often do is people will send me spectra of Vega, because and at this point I'm almost rude enough to say if it's not Vega, I'm not going to look at it, because I mean, and what he's saying is he had a little trouble. He wants to understand what's going on. This guy's really pushing the envelope in terms of what's possible. But so whether it's Conrad or me, there's lots of people out there who are happy to help you. And I get people from literally all over the world who I have the great honor of helping. So take advantage of it if it's something you think you want to do. Listen, my wife is calling me for dinner. It's an early dinner tonight.
Okay.
I want to thank you all again. It's a tremendous opportunity. I'm glad you invited me. It's an opportunity for me to share something, obviously, that I love. Thank you, Steve. Thank you all.
Thank you, Tom.
Thank you,
Thank
Tom.
you.
Francine and Jim and